So last video, we had an introduction to transformations. And I totally realized that I was more specifically talking about general transformations in the last video and not linear transformations. So, a linear transformation is just a special kind of transformation. Just like with functions, we have certain classifications for special functions like odd, even functions, things like that. We have operators that are linear or nonlinear operators. And as such, we can classify transformations as either linear or nonlinear. And so we're going to define what it means to be a linear transformation, and I'll try and give you some different things that you've probably already seen, that some operators maybe that are already linear that can help you kind of understand why we might care to work with a linear transformation. So as a definition, a transformation T, T is linear if two things. Number one, if I put in two vectors, call them u and v, into my transformation at the same time, the answer can simply be obtained by t of u plus t of v. And two, if I were to say take a scalar multiple of a vector, so let's say c times v, then I could pull the scalar multiple out and it would just be c times t of v, and where c can be any real number. So why do we care about linear transformations specifically? Because in the last video we talked how transformations, they have an input, have an output, vectors go in, vectors come out, we might be in the same space, we might be in a completely different space, doesn't matter. Why would I care about linear transformations? And let me bring up something that is not a transformation, so to speak, but a tool that we learned in calculus called the derivative. And the derivative is what we call a linear operator. And I'm not going to go through what's an operator and all that stuff, but what I will point out is that you may remember that the derivative operates this same way. For instance, if I say, what is the derivative of sine of x plus x squared, this is the same thing as taking the derivative of sine of x by itself and then adding the derivative of x squared at the end, right? That's definitely something we can do. And simultaneously, we can also, if we have the derivative of, say, 3 times x squared or something, this is the same thing as if I pull the 3 out, we can pull that constant out and take the derivative of x squared, and then, this would be 3 times 2x, which is 6x, which of course is the derivative of if we had just taken it right at the very beginning. So the derivative is what we call a linear operator. The integral works in the same way as the derivative. It is also a linear operator. And we really like working with linear operators. They follow some really nice patterns. They let us do some cool things. They're very predictable, easy to work with tools. They work in a lot of ways that you want. Maybe something as an example that's nonlinear, for instance, is just the square root symbol, right? So the square root of, say, x squared plus 9 is not just equal to the square root of x squared plus the square root of 9. This is something that we can't simplify, and there's more to be done if we wanted to try and work with this. These are definitely not the same. And so, nonlinear operators such as the square roots, they tend to leave things in messier forms. They tend to be harder to work with. There's more things that we have to kind of be careful with. So what I just showed you here was just to kind of wrap your brain around, maybe some linear or nonlinear operators you've worked with. And again, transformation is not an operator, but it, since we're talking about transformations and it has these same properties that we would be looking for linearity and these things called operators that I just talked about, I thought it was a good idea to bring them up. So a transformation T is linear if it satisfies both of these properties. So for example, you might get something that says show that the shear transformation, given, so let's say T goes from R2 to R2, given by x maps, or the vector x, let's say maps to ax, where A is equal to, we'll say 1, 0, 3, 1. Okay. Show that this is a linear transformation. Linear transformation. So what makes this a shear transformation? This word shear, it's a special kind of transformation in and of itself. We're going to go through that through this example, but I want to walk through, how we would go about and test this. So what I'm going to do, we basically need to verify that both of these conditions are satisfied, and then we're good to go. So, we need to check two things. We need to check both conditions. And we can't just check it for a specific, for just one specific vector, right? We can't just say, oh, well, let's try it for the vector 7, -4. We can't do that. To prove that this is actually a linear operator, we have to prove it for every single u and v in our space. So for all u and v in our domain, if you will, and because then the same thing down here. So in this case, since we are starting in R2, that means you might start by saying, well, okay, well, let's say, let's let u and v be random vectors in R2, such that I'm just going to say u, what does a general vector in R2 look like? Well, I'm going to say it has a u1 component and a u2 component. And the vector v, therefore, has a v1 component and a v2 component. Okay, so the very first thing that's up to bat is this first condition right here. T of u plus v is equal to T of u plus T of v. Right? We want to basically say that we don't have to add these vectors together and make it messy every time. We can kind of just deal with each one individually in the same way that we do derivatives and integrals and things like that. So we have two random vectors, u and v. And all I'm going to do first is I'm going to do the left side of this equality. So I'm going to figure out what this looks like. So let's take a look at, look at, this transformation of u plus v, okay? So T of u plus v, that is the same thing as if I did, remember that this is defined to be a times, and normally it's the vector x, but we're using u plus v here. So it's going to be a multiplied by, our u plus v vector. Now, u plus v in and of itself is going to be a new vector. It's still a 2D vector, but it consists of u1 plus v1 up here, and then u2 plus v2 here. And of course, our matrix A, this random transformation that we have no idea what it's doing yet, is 1, 3, 0, 1. I just made it up, just like if I were to pull a random function out of thin air. And so what we're really doing to see what this transformation does is we're just going to do this, transformation. We're going to pop in our input and see what we get out. So how do we do this? Matrix multiplication. Remember that we do row times column. Now, even though it looks like this might be a 2 by 2, remember this right here is just one term, and that right there is one term. Those are each an individual scalar. So there's actually only one column here. So we're going to do row times column, and what that's going to give us here when we do the first one is we're going to get u1 plus v1 plus u2 plus 3v2. That's going to be our first entry, and then the second one is going to be u2 plus v2. Okay. Now this thing kind of looks like a hodgepodge, but I'm just going to leave it there. We've handled the left side of this equality. Now, in order for this to be true, in order for it to be a linear transformation, we need the right side to hold true as well. So now what I'm going to say is I'm going to say, okay, now consider t of u and t of v separately, right? Plus t of v, okay? Well, t of u, what's that going to be? T of u is going to be 1, 3, 0, 1 times my u vector, which is u1 and u2, plus my matrix 1, 3, 0, 1 times my v vector, which is v1, v2. So if we do that, what are we going to get here? Let's see, we're going to get remember this is a 2 by 2 and this is a 2 by 1, so our result should be a 2 by 1. And so we get u1 plus 3u2, and then the bottom we just have u2. And we're going to add this to what we get in the other one, which is going to be v1 plus 3v2, and then a v2 here. And if we add these together, right, because those are just two vectors, they're both 2 by 1 vectors, we can add them together. Sure enough, if I rearrange the terms a little bit, I'll get u1 plus v1 plus 3u2 plus 3v2, and in the bottom I get u2 plus v2. And so since these are the exact same, this is the exact same as this, what we have just shown is that in general, for any random vector u and v that we could pick from R2, any random vector that we want, t of u plus v is equal to t of u plus t of v. So we've shown the first part of that the first part of linearity holds. Now we have one more check to do, which is, if I were to multiply a vector by a constant, can I just pull out that constant? That's really the last check. So the second check, so part 2, is check t of c times v, and so that's what we're going to do. And so since t of cv, well that's, again, where c is any real number. So what this is going to be, this is going to be t of, now c times my v vector is going to be cv1, cv2. Right, so that's really the vector that we're putting in. And again, right, t is represented by this matrix 1, 3, 0, 1. And now the vector we're plugging in is cv1, cv2. So what's that equal? Let's see. That equals cv1 plus 3cv2. And then the bottom, if we do row times column, we're going to get just cv2. So we get our resulting 2 by 1 matrix. And then you'll notice that every single one of these terms has a c in it, right? Every single one has a c. So this is the same thing as if I had written c times the vector v1 plus 3v2, and then a v2 here. And sure enough, if you remember from the step that we did before, this right here is t of v. So this is equal to c times t of v based on the work that we already did. And so we've satisfied both criteria, therefore this always works, okay? This is always going to work. So this transformation is indeed linear, and we have proven that. So I mentioned that this is a shear transformation. So what is it doing? So that's like a more interesting question, which is like, how do you tell what a transformation is doing? Okay, so the short answer is just like with functions. Some functions, like f of x equals x squared, they're easy to know what happens because we practice them a lot. Parabola, right? And if it's a negative, it goes down and all this stuff. But as soon as I start doing stuff like minus sine of x plus ln of x, all of a sudden our basic idea of what the heck it is and what the domain and the range is, really takes a hit. And the more complicated you make it, the more deep diving you're going to have to do. So what we're doing in linear algebra right now is we're going to kind of consider some of the more basic linear transformations. And the basic linear transformations that exist are what we call shears, contractions slash dilations, and rotations. Okay, these are like the most basic sorts of transformations. They're the equivalent of like you learn what a straight line is, you learn what a quadratic is, and that it looks like a parabola, and you learn what trig functions are, or something like that. Okay, so these are some of the more basic transformations. So taking a closer look at what this matrix is actually doing to our vectors, let's take a look at what it did, what it does when we put a vector in. So remember that we have some domain, it's R2 in this case, and we're putting in a random vector, a v1, a v2, and it's going into our transformation, so it's t of our vector v, and then what's popping out is, well, t of v. And where does that live? It lives in R2. We can check that by, again, looking at the fact that this is a 2 by 2 matrix and the thing going in is a 2 by 1. Therefore, courtesy of matrix multiplication, the result here should be some 2 by 1 matrix, and that is something that lives in R2. So we take a look at this. And what do we get out? Well, we kind of get out the same vector, but what's wrong with it? Well, the y component is the same, but the v component, it looks like we have, we've modified, excuse me, not the v component, the x component, or the first component, has been modified slightly. It looks like that we're adding some values, we're adding something to the x value, right? And so what this looks like, if we were to just kind of consider, let's say just a box that's made up of some vectors. So let's say I have a box like this, right? What's going on here? Well, it's taking all of these vectors, and what it's doing is it's shifting them more in the x direction. So the y value is not changing, but in the x direction, we're adding on some bits to it. And so what happens is you create this sort of shearing effect. So this, for instance, is a shear in the x direction, and it's very similar for a shear in the y direction. And maybe this is a good point now that I have like a visual aid, which is to talk about, where would we use linear transformations? Why do we care about these things called transformations, mapping from one thing to another? One very common example is, with image processing, right? If you want to take an image that is, maybe you have something that looks like this, right? That's sheared, maybe the scaling is wrong, and you want to do a transformation on the picture that basically assigns every single pixel in your image, it assigns it a vector, right? Where each vector, let's say this is the vector, 732 corresponds to a color and an exact position on this picture. And what we want to do is maybe do some sort of shearing transformation that turns it into a perfect square image. Or vice versa, maybe we want to cause distortion or something like that. And the other transformations, which we're going to get exposure to very shortly here, like a rotation, right? You might have an image and you want to take a vector and you want to rotate it some amount theta or something like that. That's also a transformation, and we would want to use that by, again, the computer assigns a vector to every single pixel in this image, and then it says, all right, move all of them according to this matrix. And then you get to see kind of what happens to your image. So that's just like one simple example that's kind of something we can put our hands on. Okay, so let's see here. So let's do another example. Let's do actually, before we go on to rotations, we're going to talk about, something else, which is, okay, how do we come up with the matrix A? Because as of right now, I've simply just been completely out of thin air. I've been saying, hey, there's a matrix A, it does something. And some of them, I know what they do. Some of them, I have no idea what they do, right? If I just made -2, 7 pi, and then 3 sine of 2 or something. I have no idea what this is doing. I have no idea. You could put in your 2x1 vector. I honestly have no idea. But there are some that the more you practice with, you're going to be able to be like, oh, okay, this is a shear, this is a rotation, this is a dilation. So how do we come up with the matrix A? Well, to answer that question, I need to introduce a new concept to you. And so, new concept. Maybe it's not so new if you talk about it in Calculus 3, but we have these things called the standard basis vectors for a space. And I'm specifically going to talk about in R2 for now, and then I will extend the concept. So in R2, there exists what we call the standard basis vectors. Standard basis vectors for R2. Okay. Now, those vectors, you may know what they are. They are the vector 1, 0, and they are the vector 0, 1. Okay. Now, what do we mean by basis? Basis is a word we have not defined yet officially, and not anything that I am going to define rigorously right now, but I have to bring it up in order to execute this next part of the lesson. So for now, the standard basis vectors, what we mean is that these are two linearly independent vectors that span all of R2. Or in other words, the vectors 1, 0 and 0, 1 could build any other vector in the space. So for instance, if I wanted you to build the vector 5, 4, I could do it using those vectors because I would take 5 of the first one and 4 of the second one, and I could very quickly build the vector 5, 4. So these are called the standard basis vectors, and in Calc 3 you know them as I hat and J hat. But in linear algebra, and it's fairly standard beyond linear algebra, we call these just E1 and E2. Now the reason why we don't call them I hat and J hat is because after 3 dimensions, what are you going to call it? I hat, J hat, K hat. What are you going to call it in the 4th dimension, the 5th dimension? What are you going to call it in the 2758th dimension when you run out of English letters? Whereas it's easier to use E, like these elementary basis vectors, E1, E2, and you can count forever. So in R2, there exist these standard basis vectors. And it turns out, so this is important, it turns out that to know or to create a matrix that represents some transformation T, all we have to do, or all we have to know, is what is the image of the standard basis vectors, That's all we have to know. So in other words, all we need to know is T of E1 and T of E2. All we need to know are these, and I guess those are vectors, so I'll put little bars over them. These are little vectors, okay? So T of E1 and T of E2, that's all we need to know. Because if you really think about it, if E1 and E2 can build me any vector in the space anyways, then the idea is that if I know what would happen to E1 and E2 under a transformation, then maybe mathematically speaking, I can figure out what's going to happen to any vector because I know what happens to like our building block vectors. Does that kind of make sense? So the idea being that maybe the reason why this is, so let's give a reason. This is a big theorem, and I'll try and give some justification. So again, specifically for R2, but the concept transcends R2. It's good for R3, R4, R5, any space that we are hanging out in. But the reason is because any vector X that lives in R2 can be written, and let's say x, where x is this vector x1, x2, can be written in terms of E1 and E2. So it can be written in terms of the vector E1 and E2. Specifically, what we saw earlier, the vector x can be equal to x1 times E1 plus x2 times E2, right? It's this linear combination of those standard basis vectors. And that is very useful because now when I want to know, what is t of x? What is t of x, right? What does this look like? Well, if I apply t, this transformation, to both sides of this equation that I have here, well, what do I get on the left side? I get just t of x equals, and then on the right side, I get to use the properties of linearity, right? The reason why this has to be a linear transformation t is because what I can do is I can first split these up into two separate little pieces, right? Because this is a linear transformation, so I can split this up into two pieces. And then on top of that, I can pull out, right? I can pull out that constant x1, or the scalar x1, excuse me, and then pull out the scalar x2 as well. And so what this is, if you have a very keen eye, I'll give you a minute, just think about it for a second, for like 5 seconds, right? What does this look like? Right, we have x1 times some vector plus x2 times some vector. Hopefully alarm bells are ringing. This right here is this is a vector equation that we can very quickly turn into a matrix equation. And specifically, this is going to be the matrix equation AX equals B, where what's our B vector? Well, our B, so this B is going to be, that's our T of X. What's our X vector? Well, that's the vector that consists of X1 and X2. So what goes inside the A vector? Well, the thing that goes inside the A matrix is T of E1, not a plus sign, and then T of E2, right? These are vectors. When you put them through the transformation, they become vectors. And that's it. So what this basically says is that in order to determine, right, in order to figure out the transformation for any random vector x in R2, it turns out that the matrix A that we get for our transformation just consists of, if I know what happens to the first standard basis vector and I know what happens to the second standard basis vector, then I can create the matrix A from scratch. So, for example, right, let's just run through an example. So, for example, okay, so let's say, suppose we have a linear transformation, and that's a very important requirement that these are linear transformations, because otherwise we can't do all of these tricks, and then this property doesn't hold. So suppose we have a linear transformation T that goes from R2, starts in R2, ends up in R3, and we know, right? We know that, let's say T of E1 is equal to the vector 5, negative 7, 2, which should make sense because we're ending in R3. And then T of E2 is equal to negative 3, 8, 0. Okay. So find the image. The question is, find the image of any arbitrary x in R2, right, in our domain, okay? So you might be wondering, Dylan, why do we only have two standard basis vectors? Because our input vectors come from R2, and R2 only has 2 standard basis vectors. R3 has 3 standard basis vectors. They used to be called I hat, J hat, K hat. We're just calling them E1, E2, E3. So the very first thing that we need, so what do we need? What we need is A, right? Because, you know, since T is defined by T of X is equal to AX, such that, or you can think about it as, you know, the vector X gets mapped to whatever vector we get when we do this, when we actually complete this mapping. So here, the matrix A, we already know what the matrix A is going to be like. Even though I haven't said what this transformation is, from the work we did earlier, A is simply just going to equal 5, negative 7, 2, and negative 3, 8, 0. That's what A equals, because that is the transformation of the standard basis vectors. And so once we know what A is, since we're just trying to figure out the image of any random arbitrary vector x in R2, we could say, you know, let's let x equal x1, x2 be just any random vector in R2. If you want to be super thorough, you could say x1 and x2 are any real numbers. And so then AX is equal to, you know, whatever this image is going to be. And so we can pop in the matrix 5, negative 7, 2, negative 3, 8, 0. And then we can pop in an arbitrary vector x1, x2. And what are we going to get out? So if we do this operation, we do, let's see, this is a 3 by 2, this is a 2 by 1. So we expect to get a 3 by 1 out. We expect to get a 3 by 1. And that makes sense because our output is in R3, so that makes total sense. And then we're just going to do row times column. So row times column. So for the first one, we're going to get 5x1 minus 3x2. For the second one, we'll get negative 7x1 plus 8x2. And for the last one, we get 2x1 plus 0x2. So I'll just write it as 2x1. So 2x1. And this is it. That's if you were given, so for this transformation, you know, if you were given the vector like x is equal to 1, 2, I would know without having to do this transformation 8,000 times from scratch and do a whole bunch of matrix multiplication, I could just plug in 1 for x1 and 2 for x2 and very quickly get that t of the vector 1, 2 is going to be whatever I get when I plug in those 1, 2. So if I plug in 1 for x1 and 2 for x2, I get negative 1 for the first one. Minus 7 plus 16 is a positive 9, I believe. And then the last one, I have 2x1, so that's just 2. So boom, we're done. There you go. That's what happens to this vector x1, or to the vector x underneath this particular transformation. So I think I'm going to pause right here. There's more, and in the next video, we're going to do even more examples. And where we're going to pick up in the next video is, you know, this is fine and dandy if someone magically hands you these vectors, right? If I say, well, here is t of e1 and here's t of e2, because then you can just create the matrix A, no problem. That defines your transformation, and you can solve everything. But, you know, what happens if you aren't given those? You know, what happens if you're not given the image of the standard basis vectors? You know, can you still come up with A, or rather, can you figure out what those images are and then use those to construct your matrix A? So more stuff to come, but I think for now, this is a good place to pause. So where should you be after watching this video? I think you should know what a linear transformation is. You should have a good working on how to show that something is a linear transformation. We've seen a brief example of a shear transformation, and then we went through an example or a sequence of basically trying to figure out, you know, how do we actually construct this matrix A? Where does it come from? And we found out that basically the columns of this matrix tell us that, since there's two of those, they tell us we came from R2, and those are the images of our two standard basis vectors, respectively, E1 and E2, and that's how you can build, your machine to accomplish what it is that you're looking to accomplish. So hopefully that's kind of entertaining for you all. Catch you all in the next one.